Next up is gradient and/or slope. So the simple idea here, slope is the rate of elevation decline from the headwaters or the origin of a river to the mouth, its final destination. Simple idea, we increase the slope, we increase the gradient, it's going to increase the capability of a channel of flowing water to erode, to do landform change. So some examples, deforestation in the headwater regions, one of the things as we think about trees, what they do is they do a good job of holding the sediment in. When you remove those trees, you allow much more erosive capabilities to go to work, whether it be flowing water, simply the atmospheric influences. And so what that does is then that leads to issues downstream as areas are going to be more likely to flood. So one of the things is we see rivers. If rivers go through multiple countries, the decisions made in one country definitely can affect those downstream in another country. But who cares, though, about other countries? Another thing is with the Colorado River. When we look at the Grand Canyon, like, well, how in the heck is the Grand Canyon so just massive and big? Well, the key idea there was flowing water. And so as over time, uplift, which we can go back to and talk about when we talk about plate tectonics and convergence, uplift, what that essentially did was increase the flow, increase the gradient of the Colorado River so that it then could continue to carve out the massive Grand Canyon complex that we'll probably see sometime, or we've seen in a previous lecture/slide. So here we got a profile of a river as far as going from its headwaters to its mouth. And so some characteristics we see here. As far as headwaters are where we're going to see more erosion occurring. Headwaters, characteristics, steep gradient. So when we see a steep gradient, it's going to very much carve out those V-shaped valleys. Further, minimal floodplain. And so there's, with hardly any flat, low-lying areas, there's, of course, going to be hardly any places for water just to sit. It's always going to go down slope. So especially when we have those very steep slopes. Further, if we think about, where do we go whitewater rafting? We don't go to Indiana. But wait, we got tons of rivers in Indiana. Well, where do you go? You go, of course, where you have those steeper slopes that are going to have much faster flow, and of course, a more thrilling, more adventurous ride. Characteristics we also got going on here, so we can go back and think about sediment size. Once again, going from smallest to largest. And so our largest sediments, our rocks, our boulders, are going to be found more up closer to the headwaters. As that stream gradient starts to lessen, as it starts to flatten out, of course the flow of water is going to decrease. And as that flow of water decreases, the capabilities of the sediments that can be carried, or the heavier stuff can't get carried any further. So we can kind of see how that's showcased by the gray circles here towards the middle. So there's going to be the heavier sediments. And eventually we get to the end of the general profile of a river is where we're going to have more deposition. We're going to have more sediment being laid down and actually deposited. So this kind of gives us an idea of where we would find erosion and where we would find deposition. So like I said, erosion is going to be more found at the headwaters, of course, for the various reasons mentioned in the yellow box, whereas deposition, as we'll learn here in the future slides, is going to be more found at the end of the general profile of a river. And so I highlight here the larger rocks, the larger boulders, gravel that we'd find at the bottom of a steep slope as we look at it more in depth in reality on the following slide. So obviously, very steep slope. We can, if we can imagine where we're going to see this, probably more in an upland mountainous area. But what you can still nonetheless see on the bottom right-hand side, especially, is the larger boulders, larger rocks that have been transported and deposited right here. And one of the things is, as this stream starts to flatten out, it loses its erosive capabilities and becomes more of a depositor. Now I'm going to highlight those silts, clays that we would expect to find being transported and carried beyond the headwaters, beyond the larger boulders, which we can see here, and this is actually in southern Indiana. So this is an image from southern Indiana, and we can actually see the discoloration of the surface of the water, and that's essentially what we see there is the collection of sediments from the steep slopes on both sides flowing down into this little stream. And so what we got is largely silts and clays which are causing this discoloration. So one of the things is we got to think about, okay, well, where should we build a hydroelectric power plant in the profile of this river? I'll let you think about that one. Now we see our good friend, the Colorado River. Of course, the Colorado River, as the name implies, originates in Colorado and works its way through Arizona. And so one of the things is millions and millions of years of erosion, for the most part from flowing water, has created this canyon up to a mile deep and 17 miles wide in certain parts, and actually can be viewed from space. And so the Colorado River, which today, it looks like it's just a little trickle. But one of the things is over time, like I said, millions and millions of years, flowing water has carved out very much this, clean V-shaped valley, which you can clearly see. So the canyons here are created from the flowing water from places further up, upstream, like I said, Colorado, Utah, places north or upstream from this image here. If we can zoom out, now we can really see how over time those millions and millions of years of flowing water through this area has carved out the dramatic canyon scene that we can see here. And so one of the things is we can kind of see the idea of how streams flow into bigger streams. And so you can see that a ton of these V-shaped valleys on both sides, but of course you can see that clear one that follows the current path of the Colorado River. So over time, as the river carves out deeper and deeper and deeper into this canyon area, what it does is it carves deeper into this rock, exposing these various layers. And so over time, what you can do is you can look back and see the layers from the bottom, the oldest, to the top of the canyon walls, the youngest. And so what that does is kind of gives this reconstruction of millions and millions of years of time to be able to understand better as far as where was this area, how has this area changed. And so a lot of times when we come back to understanding, how do people know what things were like 6 million, 7 million years ago? Well, a lot of it can be just revealed here in these different layers showcasing historical eras. And on that previous slide, those historical eras, I'm talking about historical geological eras, not human eras. All right, what we got here is another way we can kind of reconstruct and kind of understand, well, how in the heck is this area that's bone dry, in which it hardly gets any rain, and you can see the Colorado River today, it's just a little trickle. How in the heck has this caused and carved out such a massive structure? Well, key to understanding that is, well, it hasn't always been that way. It's not always been super dry here. If we can go back to the most recent ice age, for example, so about 10 to 12,000 years ago, we had these massive chunks of ice that were found in the Rockies. Well, these massive chunks of ice, we'll talk about this later, in places about a mile thick from surface up, so just think a mile thick sheet of ice. Well, eventually what happens is, of course, we get melting. And so with melting, of course, we're going to get this massive discharges, massive flow of water coming from areas upstream. So as that occurred, what that did was to help fill in and erode a lot of these V-shaped valleys and these canyons that, since over time, as that water is evaporated, flown, gone to wherever it's headed, essentially what it's done is it's left behind the image at the top here, which shows just a little trickle coming through here. So we have to kind of go back in time and reconstruct and say, well, actually, there was a massive amount of water in this area that relates to a previous ice age. And so now we're going to once again look at the general profile of a stream. So this is a cross-section from one side to the other. And so what we can see here is we can see very much a V shape. That's what I'm showcasing here, the V shape profile. And that what that red dot illustrates is the red dot is where we would expect to find maximum velocity, or the fastest flow of a river. So the fastest flow of a river typically is at the center, near the surface, not at the top, but near the surface, but it's always above the deepest part of the channel. And so here we can see those various things. And so the deepest part of the channel, at the center, near the surface. And so why not at the surface? Because you got friction. At the top of the surface, you get friction with the the overlying air, and so it's going to cause a slower flow, less velocity at the surface due to friction. But just below that, where that red dot is where we expect to find the fastest flow. So here we have a profile where obviously it's a different shape, but once again the red dot illustrates where we would find the fastest flow, the maximum velocity over the deepest channel. So it's what really is showcased here. And of course, this could vary as channel characteristics change throughout the course of a flow of a river. Essentially, the notes that I just spoke of on the previous slides.